Now we're going to continue our discussion of stoichiometry by looking at the useful information that we can pull from a balanced chemical equation. Recall at the end of last time that we talked about the fact that you can pull molar ratios of reactants to products or reactants to reactants or products to products from a balanced chemical equation. In this video, we'll look at the applications of molar ratios, which range from planning reactions, seeing how much product we should expect or how much reactant we need to use, to evaluating the quality of reactions through calculations of yield. So the objectives of this video are to begin with a balanced chemical equation. Remember, we talked last time about how to balance equations, and from that get the molar ratios that tell us how stoichiometrically species involved in the reaction are related to one another. We'll then use these molar ratios to plan reactions. There are two big goals that we have in the course of doing this. For one thing, we might want to obtain a target amount of product. On the other hand, we may want to consume a given amount of starting material. So if we want a particular amount of a certain product, we'll use molar ratios, or if we want to consume a particular amount of starting material, we'll also use molar ratios. Thirdly, we'll understand and apply the concept of limiting reagent. We can't simply increase the amount of a reactant without limit to increase the product that forms. We're limited by the reagent that's present in the smallest equivalent amount. We'll see what this looks like more quantitatively, learn how to identify limiting reagent, and see how we can apply the limiting reagent concept to situations where an excess of one or more reactants are used. Finally, we'll understand percent yield as a measure of reaction quality, and we'll learn how to calculate it from amounts of reactants and products that are given. Let's start by discussing a little bit about reaction planning. When in the course of planning a reaction, it's critical to use stoichiometry to answer some key questions about how much reactants we need to use and how much product we need to form. How much in terms of number of moles and thereby mass of each reactant should we use is the first question. Second question, how much product should we expect given a certain amount of reactants, either a mass or a number of moles that we're starting with? And the third question, which is more related to the validation or the assessment of how well a reaction went, is given the amount or mass of a product that we got, how well did we do in the reaction? Did we get as much product as we expected? Did we get 100% of the product that we expected? Or did we get some lower percentage? Or in cases where something has gone wrong and impurity has entered the fray, did we actually get more than we expected? How well did we do? Answers to all three of these questions lie in partially the balanced chemical equation for the process. So we'll need some given values of masses or amounts of reactants or products, but using those in combination with the information contained in a balanced chemical equation, we can calculate anything we would ever want to know about the stoichiometry of the reaction. That's the power of the balanced equation. The key pieces of information that really come out of a balanced equation are the molar ratios. And a molar ratio answers the question, how many moles of a species A are produced or consumed per mole of another species B produced or consumed? And these species A and B could either be reactants, they could both be reactants. We could, for example, be thinking about copper and nitric acid and their molar ratio. Or they could be, for example, one reactant and one product. So we could also talk about the molar ratio of copper to copper nitrate, or the molar ratio of copper to NO2. These different types of molar ratios have different purposes, but the general idea behind a molar ratio is that it allows us to convert from moles of one substance to moles of another substance that's either formed or consumed in the course of a reaction. So for example, using the balanced chemical equation at the top of this slide, we can get a plethora of molar ratios from that equation. In the matrix you see here, I've laid out species along the rows and species along the columns, and each cell is the molar ratio of the row species to the column species. Along the diagonal, we see the molar ratios of, for example, copper to copper and nitric acid to nitric acid, and of course all of these values are 1, and these aren't really very useful in the sense that we're not converting anything. That's just moles of a reagent to moles of the same reagent. But the off-diagonal ratios are extremely useful. The ratio of HNO3 to copper, for example, is 4. And this comes from the fact that the ratio of the stoichiometric coefficients, if we look back up above, is 4 to 1. There are 4 moles of HNO3 that react for every 1 mole of copper. The ratio of copper to HNO3, you'll notice, is just the reciprocal of that, 1/4, because now the ratio of the stoichiometric coefficient of copper, which is 1, to that of HNO3, which is 4, is 1 over 4, or 1/4. We can proceed analogously to generate all these other molar ratios. And each of these you can think of as a conversion factor between moles of one substance in the reaction and moles of another. So for example, we might write 4 moles of HNO3 divided by 1 mole of copper. That's a conversion factor that, because of the validity of the balanced reaction, is technically equal to 1. So we can use it to, for example, convert from moles of copper to moles of HNO3. Here are a few other examples of molar ratios that we can pull out of this balanced equation. Now, what kinds of questions can we answer using molar ratios? Well, let's think about moving from mass to moles and back again, and answering the question, given a mass m of a reactant R, what mass of product should we expect? So this is a situation where you're running a reaction and you're intimately familiar with the mass m of a reactant that you, say, weighed out. Let's imagine that this is a solid that you weighed out on a balance and dumped into a flask. What mass of product P should you expect? You might be wondering why we'd ever want to answer this question. And if you think about it, to assess how well the reaction went, we should know something about how much product we should expect. If the mass of product that we actually get is comparable to the mass we'd expect, then we know that the reaction went pretty well. How does this work? Well, it all boils down to dimensional analysis. In the diagram you see here, 2 of the paths should look intimately familiar. So moving from mass to amount, or mass to moles, the ticket to that is just moving from mass land to mole land, molar mass. And analogously, moving back to mass from amount, the ticket is once again molar mass. What's new in this diagram is moving from number of moles to number of moles, and the ticket there is the molar ratio, which has units of mole per mole, where the moles in the numerator and the moles in the denominator refer to different species. So we're converting from an amount of one substance to an amount of another, and then ultimately converting back to a mass. And we often need to do this, for example, if we're in a laboratory setting where we're going to be weighing out products and reactants, and so mass is our key sort of experimental variable. So the overall process, the first step is of course to balance the chemical equation. Once you have the balanced chemical equation in hand, there will be a given mass of the reactant R, and we can convert that to moles by dividing by the molar mass of R. Remember, that swings moles up to the numerator, puts grams in the denominator, so that the overall units after this division will be moles. We can then use the molar ratio of P to R, which we get from the balanced chemical equation. That's why that first step is essential, to determine the number of moles of P that we should expect from complete reaction of the reactant R. And finally, we can convert the moles of P back to mass. This should actually say moles of P right here, to determine the mass of product that we should expect. And this is the final step, necessary if we want to make comparisons to experimental data in the form of an experimental mass. Let's see what this looks like for our hypothetical balanced chemical reaction here. Imagine we started with 3.5 grams of copper, and we were wondering what mass of copper nitrate we should expect from complete reaction of all the 3.5 grams of copper. Well, the first step is to get the balanced chemical equation, and we've already done that, so that's in the bank. In the next series of steps, we set up what is a glorified dimensional analysis calculation. 3.5 grams of copper converted to moles, first of all. That's what's happening right here with the first factor. We then take those moles of copper, and I haven't shown the intermediate value, but we could come up with some intermediate number of moles. We take that number of moles and multiply it by the molar ratio of copper nitrate to copper, which here is simply 1 to 1. So step 3, multiplying by the molar ratio, here it's just multiplying by 1, but it's not necessarily always that simple. And then we convert that number of moles of copper nitrate now. Notice that the units are different. We've gone from moles of copper to moles of copper nitrate, back to a mass of copper nitrate. And as we've seen, the ticket there is to use the molar mass of copper nitrate, 187.56 grams. The final result is 10.33 grams of copper nitrate. And something that's worth asking is, does this make sense? Let's do a sanity check. Is this a sane result? Well, the reactant we looked at was copper, 3.5 grams of copper. Complete reaction of all of that copper should in theory incorporate all of it into the copper nitrate. Notice that copper doesn't end up anywhere else in any of the other two reactants, so it should all go into copper nitrate. But copper nitrate includes additional mass from the other atoms incorporated, the nitrate anions, right? So the expected mass of copper nitrate ought to be significantly greater than the mass of copper that we started with, and our stoichiometry calculation bears that prediction out. Given a target mass of a product P, we can also determine the mass of reactant R that we need to use to achieve that target mass of product, assuming 100% conversion. And the method here is literally identical to that from the previous slide. It's just that we're moving in the opposite direction. So we're starting here with a mass of the product, our target mass, and then we're going to a number of moles of the product. We're using the molar ratio of the reactant to the product here to get to a number of moles of the reactant, and then converting back to a mass of the reactant in the final step. And this mass of the reactant is sort of the target quantity for problems like this. So you see an example at the bottom of this slide. Imagine we were shooting for synthesizing 10 grams of water from this reaction. We can convert that to a number of moles of water first by dividing by the molar mass of water, which is 18 grams per mole, so that when we take the reciprocal, that's 1 mole per 18 grams of water. And then we use the molar ratio of copper to water here to get copper in the numerator. Notice that the water, which is what we want to cancel, appears in the denominator, and the moles of copper appears in the numerator, and here the ratio is 1 to 2. So half the number of moles of water that we'd like to form are needed to be used for the copper reactant. So half of the moles of water we'd like to form will be the amount of copper that we'll use. And then finally, we simply multiply by the molar mass of copper to get back to the final units, which are grams of copper. And we find that 17.7 grams of copper are needed to form 10 grams of water in this process.